We're going to move right along to our next speaker, Matt. Matt is going to be talking to us a little bit about some our aging infrastructure and how an innovation could help repair the face of bridges on our older bridges before they become a hazard to the traveling public. So Matt Beatty is with our Bob's Bureau, and he's an engineer working with us for about 5 years, doing a lot of good design work. So Matt, could you give us a little background on this innovation?
Yeah, thanks, Michael. Thanks for the great introduction. So I'm here today to present on a project that we worked through with Wayne State on bridge deck fascia repair. You can see here some of the deck fascia on our bridges doesn't look so good. So what the problem is the deck fascia tends to deteriorate more quickly than the rest of the bridge, which means the fascia needs to be repaired, but the remainder of the bridge is still usually in pretty good shape. There's two main concerns with this issue. One is a safety concern. Falling concrete could pose a hazard to motorists and pedestrians under the bridge. And the second concern is if the deterioration advances too far, this barrier could become undermined and then not withstand a vehicle impact potentially. The current practice in this area is to scale off any loose material to prevent it from falling. And we typically don't patch these areas because a patch could potentially pop off the same way as this delaminated material. And then if it advances too far, the result is to really repair this, we have to remove the whole barrier as well as a partial section of deck, and then recast the deck section and recast the barrier section. The purpose of the project was to develop a maintenance alternative to scaling and to identify any current details that we're using that could be contributing to fascia deterioration and develop corrective measures, to develop a best practice for long-term repair options of the deck fascia that do not involve removing the barrier because it's very costly when we have to remove that whole barrier and a section of the deck. And then also to develop best practices in design, construction, and preventative maintenance in order to prevent that deterioration from occurring in the first place. To kind of kick off the project, Wayne State worked through extensive data collection, and the first part involved a literature review. And as we really got digging into it, there really was not any previous research on this topic, but there was a few reports on similar topics, such as deterioration of the barrier itself, the deck itself, or fascia beams, but not specifically the deck fascia. The literature review after that wrapped up, it seemed to indicate there was two main causes. One of those was low-grade concrete. The other was high moisture content, particularly when that water contained de-icing salts. The next thing we looked into was a nationwide survey. We sent that out to all 50 states to see what experience they may have had with deterioration of deck fascia, and we ended up getting responses from around 20 states. This little graphic here kind of gives you an idea who we got responses from, and it's color-coded for high and low levels of deterioration. We can see here a lot of these red states in the Midwest near Michigan are all indicating they have high levels of deterioration. And that survey ended up pointing us toward a few different things that could be contributing to the deterioration. The main ones were poor drainage, poor construction practices, corrosion, chemical intrusion, and freeze thaw. We continued along, and this was one of the things I thought was kind of neat. We did some virtual site visits, so to speak. We examined 40 bridges throughout the state that were showing deterioration, and we were able to do that using photos and the inspection reports available on MyBridge. This allowed the research team to compile a large set of data without having to physically go and visit each and every bridge. And this data kind of was trending the same way as what we had looked at previously. The lower side of the bridges were showing more deterioration than the high side. The thought there is probably most of the moisture is migrating to that low side of the deck. Your bridges without epoxy-coated rebar were experiencing increased deterioration. Open railings were showing more deterioration than closed barriers. Again, you had water getting through that open railing. And most of the deterioration was featuring 3 KSI concrete, and higher traffic volumes also indicated greater deterioration. Our final step in sort of the preliminary data collection was to get boots on the ground and go out and actually visit some bridges. The team went out and visited 6 bridges, one from each region in the lower peninsula, and they took cores along the face of the barrier through the deck in order to obtain samples from right near the areas of distress. And they also set up a grid pattern so that they could examine tests as you got a little bit further away from the barrier. So they were able to conduct visual inspections, compressive and tensile strength tests, examine the clear cover on the reinforcement, check the relative stiffness, check the moisture content, run half cell potential measurements to identify if there was active corrosion there within the barrier and the fascia, and then also measure section loss on the reinforcement and also run ASR testing. When we compiled all of this preliminary information and compiled it, examined it, it came down to basically a couple of main issues. One would be a low strength concrete by today's standards, high moisture content, and corrosion. Those were the main things causing deterioration, it appeared, and those were all things that we wanted to try to remedy through the new repair. So that led us into the next phase, which was small scale testing, where we developed 4 potential repair specimens. These included a latex modified concrete, a fiber reinforced concrete, a self-consolidating concrete, and a fiber reinforced self-consolidating mix. Each of these was set up with various small-scale testing apparatuses, and they were tested for both plastic and hardened properties, so things such as slump, compressive strength, splitting strength, modulus elasticity, and shrinkage. There was also relative durability tests run on these to check for freeze-thaw, and reinforced shear tests were run to examine what the strength would be at the interface between the host material and the repair material. So that would be basically your existing bridge and your repair material, checking how well those are going to adhere to each other and not shear apart right at the interface of the new material to the old material. We got some pretty good results from that. All the materials seemed to perform well with the exception of the fiber reinforced concrete. That one, for some reason, just did not do well at all. But all 3 of the other materials featured compressive strengths and tensile strengths, which were higher than the host material. And it was thought that the fiber reinforced self-consolidating concrete was going to be the best candidate for the repair because it possessed good properties to facilitate concrete placement, which is important when we're talking about placing material near the deck fascia, because that's an area where there's a lot of reinforcement. It's very dense, so you want to make sure you can easily get material to flow into those areas without getting any type of separation in the concrete mix. That mix also sustained the highest tensile strength, and it appeared to sustain compressive and tensile loads after initial cracking. So that's important again in this area we're looking at along the deck fascia, because it suggests that if any delams do start to occur, it's going to retain those concrete fragments and potentially prevent them from falling. The self-consolidating concrete appeared to be a good candidate as well, and it had the second highest tensile strength. That led us into the full-scale testing. That was going to be our final stage in the project. You can see a picture of the full-scale testing apparatus here. Basically, what it represents is we have a section of deck here, and then we have a barrier on either side, and these 2 sort of wings at the top with a jack in the middle, so we can transmit load up here at the top of the barrier in order to flex it outward, similar to a vehicle impact. We were able to create 3 of these full-scale models like this. One represented a control specimen, just as if it were a new bridge, essentially, no deterioration, no repair. And then one repair specimen with the fiber reinforced self-consolidating concrete, and one repair specimen with the self-consolidating concrete. And what that looked like was we came in here, and this material along the back corner of the barrier was removed to simulate a deteriorated fascia that had spalled away and left a undermined barrier. We then went in and adhesive anchored in D-bars alternating directions. So what a D-bar is for folks not in bridge design, that's a piece of reinforcement that basically it has a hook on the end. So you would adhesive anchor it in and you'd have this nice hook like this so that we could then pour the repair concrete and restore the geometry so that it looked exactly like it would have in the initial condition. All three of these were then exposed to accelerated weathering and accelerated corrosion to simulate years in the field, and then they were loaded with that jack until failure. The results ended up being very good. Both specimens were able to restore the barrier to a TL4 crashworthiness, which is consistent with what we test our barriers for. And both barriers failed just slightly less than the control specimen, but still very close to it. So this showed us that these repairs were almost as new as good, almost as good as new. And then after taking a further look, the fiber reinforced self-consolidating mix was deemed to be the best repair due to the concrete's ability to maintain those compressive and tensile loads even after the first cracks, because again, the hope is that that will be able to retain any concrete fragments if any cracking were to start. So to summarize, what we managed to get out of this project were two different repairs. If the barrier is not undermined, then the plan would be just continue scaling the way we do, but apply a polyurea coating, which would protect the area from moisture and potentially prevent it from getting worse. And then if the barrier is undermined, then they could install the proposed repair as we saw from the large scale testing. One of the cool things that was developed as well was a computer program which could be used to determine if the barrier has become undermined. So for here at MDOT, that would be a nice help in the current process, because currently the way we do things is if a region inspector goes out, notices some deterioration of the fascia, they'll submit an RFA, which is a request for action, and then a design unit will take a look at it and analyze the barrier to see if it's undermined. With this new program, it would allow the region to quickly input the level of damage and see right away if it's undermined. So it would just kind of speed up the process and also add some consistency to the way folks are analyzing that deterioration. The other thing that was developed was a draft special provision. So that special provision would be able to be utilized in a contract and defines the concrete mix and the way in which the reinforcement is installed so that we can implement this on a project potentially. And the final thing that was examined was several different options were looked at to try to prevent that moisture from getting to the fascia in the first place. So those consisted of several different alternate water stops, such as elevated and suppressed shear keys. And the thought there was those might be an improvement over the current water stop we use. And if we can prevent that moisture from getting to the deck fascia in the first place on new constructed bridges, that would potentially prevent the fascia from deteriorating in the first place. So that sort of concludes the project, and I'd ask if any folks have any questions.
Thanks, Matt. Appreciate your presentation. Just ask you to monitor the Q&A section of this live event to see what questions are there and type the answers there. Yeah, if anybody's got some aging bridges out there in your region or your county with deteriorating concrete in the face, sounds like Matt's got some solutions involving fiber reinforced self-consolidating concrete and polyurea spray on that could be helpful for you. Maybe check in with Matt and he could give you some advice.